Hello, very good day to everyone. Today we will look at the new topic, which is actually um, we should cover this on week 12, but we are a bit late, but no problem. But this topic is very important for you. It will come out in final exam. The topic related to this will come out in final exam. So the topic today is the solving the general solution. You can find the notes in the spectrum, yeah. The general solution of partial differential equation, PDE. Okay. We need to cover two things here, which is solving the general solution. So general solution, you will not have a boundary condition or the initial condition that I will show you later, and particular solution is in the case where you have the boundary condition or initial condition. So in general condition solution, you will have like a coefficient or unknown, like for example a, b, c, and then in particular solution, the question will give you the boundary condition or initial condition. So you can find what is the value of a, b, c, maybe 3, b, 2, c, x. All right. So in differential equation chapter, you have learned how to differentiate between the ODE and also PDE. Okay, how it's to classify them in terms of order, linearity, and homogeneity. And in simple, I can say that so you also learned about homogeneous and non-homogeneous. Homogeneous meaning that it is equal to 0. Non-homogeneous, it is not equal to 0. And the difference between the ordinary differential equation and partial differential equation. This is partial differential equation, and then this is ordinary differential equation. That the ODE, it involves derivative with respect to one independent variable, one independent variable, like uh, d dx, d dy. So it is related to one independent variable. Meanwhile, for the partial differential equation PDE, it involves partial derivative with respect to two or more independent variable, two or more independent variable. For example, du dx plus d squared u dy is equal to 0. Okay. So the application for the ODE is usually population growth, electrical circuit, and then for PDE is like the heat condition. We will cover three things here, which is related to Laplace equation, heat equation, and wave equation. Okay, so the solution usually in the single variable for ODE, the solution easy to solve at ODE actually. So the solution will be in single variable. For example, yx is equal to what? But the solution for partial differential equation usually will be in multiple variable. Like for example, u, x, y. You will see throughout this topic. Yeah. So the general equation for the PDE is given as you don't need to remember this actually. Du dx plus b d squared u dx dt, usually related to time, d squared u dt squared plus d du dx plus e du dt plus fu equal to 0, where all these a, b, c, d, e, and f, they are all constant. Okay, but you don't need to remember all of this, right? Okay, the general solution in terms of unknown, we can say that this is all converted into this u total equal to u total of x and t, because you see here it's in term of x and t, yeah. Okay, and then equal to the summation of from n is equal to 1 a 3 n cos n pi t sine n pi x. Okay, so if you see here these things, right, is comparable to the last topic. So you need to know that this topic is linked to the last topic with the Fourier expansion. Okay. Okay. Um, Now I want to show you that we can actually 1 minute. Yeah. Okay, there are three categories. There are three categories of second order linear homogeneous PDE based on b squared minus 4ac. So there are three categories of second order PDE. Okay, so the first one is it is all based on b squared 4ac. I think remember you learned this in the high school, I think. Okay, so the first one is is elliptic PDE. We call it elliptic PDE when b squared minus 4ac is actually less than 0. All right, 1 minute. And then here we have the second category, which is the parabolic PDE. B squared minus 4ac is equal to 0. And then we have hyperbolic. Okay, hyperbolic PDE. Now b squared minus 4ac greater than 0. Okay, the difference here is, sorry, here it is less than for parabolic is equal, and for hyperbolic it is more than 0, right? So for the elliptic PDE, okay, for the elliptic PDE we use Laplace equation. Okay, Laplace equation. So each of this category of PDE is further divided into one dimension, two-dimensional, and three-dimensional. So, but we will look at this first, where for elliptic PDE we usually use Laplace equation, which is you need to have this in your support sheet. Okay, make sure you have all of this. Okay. Okay, d squared u dx, d squared u dy squared is equal to 0. So the characteristic for the elliptic PDE, it is steady state. You need to see in the question if it is mentioned steady state, meaning that it is elliptic PDE. Okay, and then it is also time invariant. Time invariant, if you can see from here, there's no t, so it is time invariant. It did not change with time. And then, for example, is you want to find the stable temperature distribution of a heated or cooler plate. So this is like a plate. You want to find the temperature at this point, for example. So you use elliptic PDE. To solve the problem. And then we have parabolic PDE, where b squared is minus 4ac is equal to 0. Usually this one we call Laplace equation. This one we call heat conduction equation, or heat equation. You can just call it heat equation. Okay, heat equation. And heat equation, it is we use this equation 3d squared u dx squared is equal to du dt. If you see dt here, we know that it is time variant. Time variant change with time, but it is non-oscillating. Okay, so we need to find what is the value of u x t, and meanwhile here we need to find the value of u x y. All right, so for example of a problem related to parabolic PDE is you need to find the temperature of a heated or cooled 1D road that change over time without oscillation. Like for example, this is a big road. Okay, you need to find the temperature. So you put some heat here. Okay, the heat conduction will happen, and then you want to see what is the temperature at this point at what time. All right, and then we have the last one, the parabolic, which is very important in your final exam. Okay, b squared minus 4ac, which is greater than 0. We call this as wave equation. All right, wave equation. Okay, d squared u dx squared is equal to the squared u dt squared, and you need to find the value of x and t. So whenever you see t, you know it is the characteristic of it is time variant. It is changing with time, but just now we have time variant but non-oscillating, but now here for the wave equation, because this is related to wave, it is oscillating. Okay, for example, the question related to the hyperbolic PDE, you need to find the vibration. Vibration you can see related to the string. For example, for the musical instrument, you need to find vibration of string. Okay, if you see the question related to the vibration of string that change over time, and then with oscillation, you know this problem is related. If you find these 2 point time invariant and it is oscillating, you know it is related to hyperbolic PDE, and you need to use the wave equation. Okay, there are 3 types of wave equation. Later I will show you. There's one-dimensional, two-dimensional, and three-dimensional. You need to focus on the one-dimensional hyperbolic PDE. Okay, so I will just want to share with you d dt is equal to time variant. Yeah, okay. So for elliptic PDE, okay, we go for elliptic PDE first. So elliptic PDE, we have also one-dimensional Laplace equation, two-dimensional Laplace equation, three-dimensional Laplace equation. Okay, so for each of them, okay, for each of these Laplace equation, one-dimensional, two-dimensional, and three-dimensional, they have different equations. So the equation for one-dimensional is d squared u dx squared equal to 0. So you need to find what is the value of ux, and then for second two-dimension Laplace equation, that for example this is the sheet one just now, right? The metal sheet. So this is one-dimensional, two-dimensional du dx plus d squared u dy squared equal to 0. Here you need to find the at coordinate u and y. Okay, and then three-dimensional, you will have something like this, for example. So you will have the formula that you need to use is d squared u dx squared plus d squared u dy squared plus d squared u dz squared equal to 0, and then you need to find at the point of u, x, y, and z. Okay, so the important one in the elliptic, the thing that you only need to learn in this topic is the two-dimensional Laplace equation, where we can solve this using separation variable. I will show you the method of separation of variable, which is very important in your final exam of variable. Okay, please focus on this. So separation variable will not only use for the elliptic PDE but also for the parabolic and hyperbolic method also. Okay, so but if you can refer to the lecture note, you can see all the formula, all the equation that will be used for one-dimensional, two-dimensional, and three-dimensional. But for elliptic, you just need to focus on the two-dimension. And for the parabolic, you just need to focus on one dimensional. So parabolic, you know, it is heat equation. Anything related to heat, it is parabolic. One dimensional heat equation. Okay, the equation that is related to it, 1 over c squared du dt equal d squared u dx squared. Okay, and then the strategy, you need to find the value of xt. You need to find you can solve this problem using the separation of variable. Okay, and then for the hyperbolic PDE, okay, which is related to wave equation, you really need to focus on the one dimensional. So two and three dimensional, you don't need to look at for this subject. Okay, one dimensional wave equation. Okay, the formula that you need to have in your cheat sheet or the supporting sheet is d1 over c squared. Okay, and then d squared u dt squared, sorry, equal to d squared u dx. I'm sorry, this is the wrong equation. Okay, so for hyperbolic wave equation, the equation for hyperbolic PDE is 1 over c squared d squared u dt squared equal to d squared u dx squared. Right? So also the method to solve this is using separation of variable method. Because we are looking at separation of variable method, we only look at the one-dimensional wave equation, one-dimensional heat equation, and also two-dimensional Laplace equation. Okay, the other two-dimensional and three-dimensional, they are using the other method to solve this, so we will not cover in this topic. Okay, so all of this, the question that we will cover in this topic is only for the uh, homogeneous PDE, or non-homogeneous we will not cover in this subject. Okay, if you want to know the difference between non-homogeneous and homogeneous, you know that homogeneous, the right hand side will be equal to 0, while non-homogeneous, it will not be equal to 0. It is a little bit difficult to solve actually. Okay, now we will look at the method that I'll show you how to solve the equation using the method of separation of variable. Separation of variable method. Okay, for second order linear homogeneous PDE problem with constant coefficient, like for example, I show you the long equation just now. The a d squared u dx squared plus b d squared u dx dy plus c d squared u dy squared plus d du dx plus e du dy plus fu is equal to 0. Okay, for second order, this is second order linear homogeneous PDE with constant coefficient. All the A's until F, they are constant coefficient. we can assume it to be, we can assume that our solution is to, in terms of x and y, and then can be separated into x and y function respectively. Okay, we can separate it to x and y function respectively. Okay, so you need to familiarize with all of this, like for example du dx. All right. du dx, it is equal to, now with respect to x, right, you can see that it is respect to x, so you can have dx x, okay, dx y y. It is actually equal to, you can see our x is here, right, so x prime, and then we just add y here because it is, we also have y in the equation. Okay, now we have d squared u dx squared. You see we have x here, but it is to the power of 2. So you can have x double prime y. And then d squared dy is equal to, we have y here, so y prime, and then just add x. And then we have d squared u dy squared. So this is, you know that y prime and x. Okay, and then we have, like for example, we have d squared u dx dy. So you can know that this is x prime and y prime. Simple. Okay, so you can reduce all of this into, okay, a x x double prime, okay, y plus b x y plus c. Okay, so we have y there, so x and y double prime plus d, so we have x prime plus x prime y plus e x y prime plus f x y is equal to 0. Simple. So if PDE can be simplified into, or we can also further separate it, because we want to separate it into x and y, right? So you can bring all this y together, like this is y, this is y prime, this is y double prime, this is y. Okay, we can simplify it into y ax double prime plus dx prime plus fx plus y prime bx prime plus ex plus y double prime cx equal to 0. So now we can simplify this. We can simplify c equal to 0. C equal to 0, and then b and e equal to 0. If c is equal to 0, right? So we have y ax double prime plus d x prime plus fx plus y prime dx plus ex equal to 0. Okay, we can rearrange. Okay, we can rearrange this. So we bring all the y to one side. So y, bring here, you can have y prime over y equal to negative ax double prime plus dx prime plus fx divided by bx plus ex. So equal, we just make it equal to negative lambda. So we need to assume that it is equal to separation constant. So this is the separation constant of lambda. Okay, so usually in this method of separation variable, we separate each of the um, y and x into one part 1, this is part 2, and then we make it equal to the separation constant. So this one will be equal to this one, and this one will be equal to this one, and finally we can have two ordinary differential equations. So from one PDE we can convert it into two ODE. ODE 1, ODE 2. This one difficult to solve, but ODE easy to solve. And the method we are using is separation of variable. I will show you now how they do this. Okay, so here our first ODE is actually from here. Okay, so y, just like, okay, our ODE number 1 is y prime over y, which is this one, equal to negative lambda. Okay, so we can bring here y prime minus lambda y plus lambda y equal to 0. So this is ODE number 1. And then we have ODE number 2, which is the long one, this long one. ODE number 2, negative ax plus dx plus fx divided by bx prime plus ex equal to negative lambda. Okay, you can bring this one here, so you can have ax plus dx plus fx equal to negative lambda bx plus lambda ex. So now you can separate it with, you can like factorize it with the x. So we have x a double prime, and then we have this and this. So d minus lambda b x plus f, this one and this one, f minus lambda e x equal to 0. This is ODE number 2. Okay, so like I said just now, we have one PDE. We use separation of variable method to have ODE 1 and ODE 2, so we can solve it easily. Okay, now we will look at how to solve the question. Okay, so separation constant negative lambda can solve the problem easier. We can solve the answer using three cases. After this is the first step, which is separation of variable, and then after we do all of this, we need to solve the problem using separation constant that may be, this separation constant may be equal to 0, may be negative, or may be positive. Okay, we can get 3 PDE solution from 3 cases, which is a case number 1. Usually this is, we call it case number 1, where lambda is equal to 0. And then we have case number 2, where lambda is equal to negative a squared, where a is greater than 0. And then the third one, we have case number 3, where our lambda is equal to positive a squared, where a should be greater than 0. Okay. Okay. Now maybe we will look at one example. Okay. So the example here is solve the general solution. General solution meaning you don't have to insert boundary condition to get the final answer. So your answer can be can have like constant the like a unknown constant like a until f. Okay, so solve the general solution of PDE below, of this PDE, using separation of variable method. Okay, so we have d squared u dx, okay, equal to 4 du dy. Maybe the question will ask you this equation based on the three elliptic, which is Laplace equation, heat equation, or wave equation. They will give you all this. If you know this equation, then you know how to use how you can get the answer, because you know the equation. Okay, so step one, what you need to do is you need to use separation of variable method. Okay, okay, how? We first need to let uxy equal to x. Okay, and then we can convert this. If you can see here, it's x squared, right? So you will have x double prime y plus 4, sorry, equal to y prime, and then we have x. Okay. Sorry. Okay, and then step 2, we need to obtain 2 ODE, 2 ordinary differential equation from this one PDE. So we need to use separation of variable, meaning that you put x one side, y one side. So we have x double prime, we bring 4x here, so we have 4x equal to y prime over y equal to negative lambda our separation constant. Okay, so we can have ODE number 1, x double prime 4x equal to negative lambda, and ODE 2, y prime over y equal to negative lambda. So this is equal to y, x double prime plus 4, because this one will bring here, 4 lambda x equal to 0, and then x double prime plus 4, y plus lambda y equal to 0. So ODE 1 and ODE 2. And then step 3, you need to solve using 3 cases of lambda, which is lambda equal to 0, lambda equal to negative a minus, and lambda equal to positive a minus. So it is easier for you to, why like I have all the square, yeah? I don't understand. Okay, so it is easier for you if you make a table, like for example, for case number 1, you can like make this is table for y, this is table for x. So we have for y just now, we have y plus lambda y, x double prime plus 4 lambda x equal to 0. Okay, now if we have our lambda is equal to 0, right? What will happen is that we will have y prime equal to 0. And then, okay, before that, I need to explain to you that we usually, for this question, we usually assume our solution of x equal to e to the power of rx, where r is the root. Okay, so when we have this, we need to change it to, we need to let r become the root, and we will use the characteristic equation. Okay, now I'll show you how. Okay, so our r, we will replace our r, we will find our r, and when we will substitute it here. Okay, how you can do is, okay, now our y is equal to 0, our y prime is equal to 0, and then we change it to our characteristic equation of CE. Our characteristic equation for this, if y, it will become nothing. You just cancel it, it will become 1. If y prime, it will become r. Okay, so here is y prime. Our characteristic equation will become r equal to 0. Okay, if y double prime, we will have r squared. Okay, and now r is equal to 0, meaning that our y is equal to c. We usually put some constant c1, start from c1, e r y, erx, right? But because this is in term of y, we put c e to the power of ry. But our r is 0, e to the power of 0 is 1. So we have c1 here. So y for case number 1 is c1. Okay, let's see what happened to x. So here for x, our let r equal to root, and then our characteristic equation, when we substitute this lambda as 0, we will have x double prime as 0, and we have our characteristic equation, which is this is x double prime. We can have r squared is equal to 0, r equal to plus minus 0, so r1 is 0, r2 is 0. Okay, so also I need to show you now here, we have for second order ODE, in case we have our R1 equal to R2, like our case now, R1 is equal to R2, so this is we call a repeated root. Repeated roots, so our x will become C1 E R1x plus C2 ER2x, but because it is a repeated root, we must substitute x here. But if R1 is not equal to R2, here we call that for this case of distinct roots or complex conjugate roots, our x total will be equals to CERYX plus C2ER2X. So no extra x here. The only difference is the repeated. For repeated root, we need to have x here. So for our solution here, our x total will be, because this is the repeated root, so our x total will be C2 E R X, okay, plus C3, because we start with C1, C2, C3, E X R2 R3 X, okay. But because our R0 e to the power of 0 is 1, we have C2 plus T3x. Alright. Okay. Next we need to continue for our case. This is case number 1. Our case 2, where our lambda is equal to negative a minus squared, where a is greater than 0. So just now, we have y prime plus lambda y equal to 0, x double prime plus f lambda x equal to 0. Now we need to substitute negative a squared to this lambda. So we will have plus a, it will become negative a squared y equal to 0. Then we change to our characteristic equation. Our characteristic equation, this y prime will become r minus a squared, y will become 1 equal to 0, r equal to a squared. So our y is equal to c, just now c3, now we have c4, e to the power of ry. So r is a squared y. Alright, and then for this one, x double prime plus 4 become minus a squared x equal to 0. Our characteristic equation is equal to r squared minus 4a squared equal to 0. Our r squared is equal to plus minus of 4a squared. So our r1 will become 2a and our r2 equal to negative 2a. Okay, so our x is equal to C5 E 2ax plus C6. Because this is not repeated, we don't have extra x here, 2ax. Okay. Oh, before that, for case number 1, we can say that y x y this is what we call its PDE solution for case number 1. So this is u1 equal to 1 equal to, we just multiply this and this, so we have c2 plus c3x multiplied by c1, or we can like simplify it into a1x. So a1x is c1 c1 multiplied by c3, we have a1x plus c1 multiplied by c2, we have b. And then we can say that a1 and b1 are equal to constant. Alright. Now, for case number 2, now we proceed for case number 3. Okay, for case number 3, where lambda is equal to positive a squared, where a is greater than 0. Okay, our y will replace positive a, lambda to positive a, will get this, and then let r be the root. Our characteristic equation will become equal to 0, and our r is equal to negative a squared. Then our y will become c7. Now we stop at, or before that, hmm before that, we, for this case number 2, right, for PDE solution, for in case number 2 is u squared minus equal to x2 y2 equal to c5. We just multiply this and this one, we have 5. c5 e 2ax plus c6 e9 to the power of negative 2ax. Then we multiply it by simply c4 e a squared y. Anyway, okay. And then our u2, we can simplify it to a and b, but in terms of 2, okay, we can factorize this a squared y, and then this c4 multiplied by c5 and c6, it will become a2, then e2ax plus c4 multiplied by c6, we have b2, y b2, just now is we have b1 and a1, now a2 and b2, e to the power of negative 2ax, where of course the same a2 and b2 are equal to constant. Okay, now for case number 3, we have C7E. We continue ERX, ERY. So our R is negative A squared, then Y. Okay, and then for here, for X, we have X. We replace lambda to the positive A. We will have 4a squared x equal to 0, and let r be the root. Our characteristic equation for this will become r squared plus 4a squared, so x will become 1 equal to 0. Then our r, okay, now if we go here, it will be negative. The square root of negative is a complex conjugate root case where you will have imaginary function as your answer. So we have plus minus of square root of negative. I remember, I know that you learned this in form 5 or form 4. So when you square root negative, you will have complex conjugate root cause, where you will have r1 equal to positive 2ai imaginary function, and your r2 is equal to negative 2ai. So your x is equal to now c7, c8, okay, e to the power of 2axi, okay, 2a xi rx. Okay, now you have additional I here, plus c9e, then here is negative 2axi. Okay. Oops. So next, what you need to do is u3. What is your u3? u3 is equal to x3x, y3y. So you just multiply this and this, you will get C8e to a xi plus c9 e to the power of negative 2axi multiplied by c7e negative ay a squared y, and then you multiply c7 and c8, multiply c7 and c9, you will get a squared y, then a3 e 2axi plus c9 multiplied by c7, you get b3e to the power of 2axi, where of course a3 and b3 is equal to constant. Okay, now we have the solution for all the 3 cases. Okay, so we have case number 1, we have this, and then for case number 2, we have this, and case number 3, we have this. So to find our final answer, we need to use superposition theory. Okay, superposition theory. principle, superposition principle. So just now you have ui, u1 plus u2 plus u3, right? So our final final answer is 2xy equal to case number 1 plus case number 2 plus case number 3. And it is equal to a1x plus b1 this one, and then plus this one, case number 3 and case number 3. Okay, so this is case number 1 plus a to y a to e to ax plus b2 e to the power of negative 2ax. This is for case number 2. Plus e to the power of negative a squared y a3 e to ax1 plus b3 e to ax1, and this is case number 3. Okay, now if you look at the solution, it is very messy, not very easy to handle. So there is a method that can help you to express this PDE solution in terms of cosine and hyperbolic cos, which is COSH, hyperbolic sine SINH. Okay, we can't if your answer is related to the exponential or complex conjugate, okay, of complex conjugate, meaning that your answer is in term of I, imaginary function. For example, you have just now a3, right? E to ax y I plus b3 e negative 2ax I. So this one you can convert it into, actually all the number you can just put any alphabet, okay, C, D, or anything. So because we just use A and B, we don't want to be confused, we put C now. So C3, 3 mean that case number 3. Okay, C3, so if you have complex conjugate, so you have this one, this is the I, our R is 2A. Okay, so anything with complex conjugate, you can convert it into cosine 2ax plus now d3 sine 2ax. Alright, but this is for exponential or complex conjugate. But what if your answer has no complex conjugate? Okay, for exponential mean e to the power of I, but this one e not to the power of I. Okay, of distinct root, distinct real root. Okay, for example, we have for a2 just now. For a2, we have e to ax, no I, you see. Here we got I, here we got no I. plus b2e to the power of 2ax equal to, so here our r is this one, right? You just think about, you don't need to think about negative or positive now. You just get the, now c2, just change to hyperbolic cos. Plus, now, sorry, d2 sine, hyperbolic sine 2ax. Okay? Now, this is the general solution. Just now I mentioned to you that we can. So all this general solution is in term of C, D, all this alphabet. But we need to find the particular solution. Meaning particular solution, we need to insert the boundary condition or initial condition for us to get the particular solution. Now we look at the initial and boundary condition, which is also very important in your calculation of for this type of question. Boundary condition of PDE problem. Okay, like I mentioned just now, after very long calculation, your answer is still in term of unknown, which is A1, B1, A2, B2, A3, B3. Okay, so by using initial and boundary condition of PDE, you can solve those unknown. You can get the value of those unknown. And then when you get the value for that unknown, the solution is already in term of particular solution. So there are three types of boundary condition that are found to occur most regularly, which is the first one is Cauchy condition. You will not understand it now, but I will show you an example. So for Cauchy condition, you have u and du dn. It is given on C. This is for Cauchy condition. And then the next one, we have Dirichlet condition, which is only u is given to you. And then we have Newman condition, which is du dn is given on C. Okay, a boundary C is said to be closed if conditions are specified on whole of it, or open if conditions are only specified on part of it. Okay, so we look at one example. I will show you after this. Like for example, okay, I will show you now. Now, for example, we are looking at the Laplace condition, the Laplace equation. So Laplace equation for the b squared minus 4ac is less than 0. So you need to focus on two-dimensional Laplace equation, right? So for example, we have a region of a 2D plate. So 2D plate, we have x and y. Okay, so we have, this is for elliptic problem. Okay, elliptic, we use Laplace equation. We need to set up the boundary condition. BC is boundary condition. Boundary condition of steady state temperature. This is the question, yeah. steady state temperature. So when you see steady state temperature, meaning that the keyword will bring back you to the elliptic problem of u, x, y for a rectangular plate. Rectangular plate coincide with the region defined by, so our x is from 0 to 4 and our y is from 0 to 2. Okay, the left end and the right bottom of the plate, left end left end of the plate and the bottom are insulated. Okay, when it is insulated, you know that you need to remember our du dn is equal to 0. The top of the plate is held at temperature 0. Temperature is equal to 0, meaning that this is u is equal to 0. And the right end of the plate, is held but at a temperature equal to Fy. So u of the right end is equal to Fy. So the PDE governs the problem given by Laplace equation. You remember Laplace equation, 2D Laplace equation. D squared u dx squared plus d squared u dy squared equal to 0. So how we need to present this problem. Now you can say that the corresponding region of the boundary condition in xy plane was steady state heated rectangular plate. So you can have this. So we have A, and then this is might be our x is from 0 to 4, and then our y is from 0 to 2. Okay, so we have B, we have C and D. Okay, so now from the point that we get from the question, it is saying that our left end and bottom end are insulated. So left end and bottom end are du. This is because this is y, this is x. Okay, this should be in the red, or what is not changing is x. Okay, x. So du dx is equal to x is equal to 0. So because our it is insulated, so du dx, but this one in terms of du dy is equal to 0. I will show later why. And then our top temperature u equal to 0, right, and temperature is equal to Fy. Now, just now I mentioned to you, if you have this one, it says Newman, right? Newman condition. Okay, so this is Newman on the left and bottom, Newman condition. This one also Newman condition. But this one, u is equal to 0, u given is Dirichlet condition. So this one is Dirichlet, this one is Dirichlet condition. This is Dirichlet, this is Dirichlet, this is Newman, this is Newman. Okay, so how to write our boundary condition? So we have Dirichlet for the top and right end. From the top, we have U, okay, but it is on top. So here, from traveling from here to here, it is along the y-axis, along the x-axis, and then at point y equal to 2, okay, is equal to 0. And the right end, you see the point is traveling from 0 to 2, so it is along y-axis. So along y-axis, at what point this is x is equal to 4, equal to fy. Okay, we can also say 0, this is ux comma 2 equal to 0. From 0 to 4, this is y, our y is traveling from 0 to 2. Okay, easy. And then we have the Newman condition. Newman condition for the bottom and left. So our bottom is du, because it is along the x-axis, so it is along the x-axis, and the y, this is here, right? So this is along the y-axis, and it is at y is equal to 0. Okay, then the y, so we can have du d y, sorry, this should be du dx. So for bottom du dx. Okay, so for bottom, yeah, it's right actually. So for bottom, du dy of x, and then y is 0, so d squared dy at y is equal to 0, is equal to 0, 0, 4. Okay, right. And then for the left part, this part, right? So d squared, because it is along the y-axis, right? So 0 at x0 along the y-axis. So this one dy dx equal to du dx. And then our x is equal to 0, because x is equal to 0 here, is equal to 0 from 0 y2. And then the heat flux cannot flow in x direction, qx is equal to 0. If there is insulation, okay, the heat flux cannot go, because we insulate this bottom and left, so the heat cannot go. Alright, now this is the method of finding the boundary condition for the Laplace or elliptic problem, elliptic category. Okay, we will also look at the how to find the boundary condition for parabolic condition. Parabolic condition, like I said just now, b squared minus 4ac will be equal to 0, and usually we call this as heat equation. Okay, now the question, for example, now we have one example, a rod length L coincide with the interval of 0, L on the x-axis. Set up the boundary. The question asks you to set up the boundary value problem for temperature. When the left end is held at temperature, left end is held at temperature 0, and the right end is insulated. The initial temperature Fx, so this T is actually for time, yeah? The initial temperature, not temperature, it's time. The initial temperature of Fx the initial temperature is Fx. Throughout, the PDE governed the problem of one-dimensional heat equation. So you know, when you see one-dimensional heat equation, you go to the table, just now get the formula du dt. Just now they put C down here. I can just change C anywhere. Du dx squared, where C is the constant. So ask us to formulate the initial condition of the one-dimensional bar that change over time. Okay, now temperature of one-dimensional bar that change over time. Okay, now the corresponding region of the boundary condition in xt plane for the heated or cooled bar. So we have one bar here. Okay, so left end temperature is U is equal to 0. This is X equal to 0. And then this is X equal to L. And then the right end is insulated. Du dx equal to 0. So this is only like x-axis, so du dx. Okay. So now I can tabulate it into like a graph like this is. Like here insulated, right? So insulated, we have U is equal to 0. So this is Dirichlet condition for U equal to 0. And then sorry. So, oh my god. And then we have the initial temperature throughout is Fx. So throughout all the time, the U is equal to Fx, which is given. So this is Dirichlet condition also. And then at the end, we have Newman condition. Because it is insulated. So here, our Dirichlet condition for the left end, okay, the left end, okay, is U0 T equal to 0, where T is greater than 0. And then dirichlet condition for the initial temperature here. So u x at time 0 is equal to fx. Okay. And then the Newman condition at the right end is ux l t du dx x equal to l equal to 0, t is greater than 0. And now we will also look at the hyperbolic PDE. Okay, so hyperbolic PDE is related to, like I said just now, is oscillating and then also time variant. So for example, a string of length L coincide with interval 0, L on the x-axis. I think some problem with my iPad. Okay, for hyperbolic category, I will share with you in the next video, and then please watch the next video also. Okay, hope you can see that the problem that we have in this topic, that we have a very long calculation. So you need to know, the first thing you need to know the formula for each of the category. Very important for you to have that formula. And then the important thing for you is to know separation of the variable method. How could you bring all the like x to one side and then y to one side, or if in the exam you have other alphabet, just bring each of them to the one to one side and then make it equal to the separation constant, which is negative lambda. And then you know that from that you can get two ordinary differential equation. From one PDE you will get two PDE, so that for easy for you to solve. So how can you solve these two ODE is by applying three cases, where cases 1 lambda is equal to 0, case 2 lambda is equal to negative a squared, and case 3 lambda is equal to positive a squared. And from each of them you will get the solution u1, u sub 1, u sub 2, and u sub 3. And u sub 1 is equal to x multiplied by y of 1, u sub 2 is equal to x sub 2 multiplied by y sub 2, and then u3 is equal to x sub 3 multiplied by y sub 3. And then the final general solution is the combination of u1, u2, and u3. And then the solution will not end there. You need to find boundary condition, which is not yet I need to explain more on the boundary condition, which is also very important for you to get the particular solution from the general solution. You have general solution, you substitute initial condition or boundary condition, after that you get particular solution. Okay, all right, I will continue in the next video. Hope you can understand. Please try to revise and do some example on this. Thank you. Thank you for watching. Bye.